Welcome to the next installment of The Last Word, an AALAS podcast. My name is Jennifer Smith, and I'm the Director of Education and Scientific Affairs at AALAS. With me today is Dr. Daniel Pang. Daniel is a diplomate of the American and European Colleges of Veterinary, Anesthesia, and Analgesia. He's currently a professor and veterinary medicine faculty member at the University of Calgary. Dr. Pang also serves as the co-editor-in-chief of the journal Veterinary, Anesthesia, and Analgesia. He is a respected and frequent contributor to the scientific literature on veterinary anesthesia and pain. Daniel, how are you doing? Please tell us a little bit about your background.
Hi, Jennifer. Thank you very much for the kind introduction, and thank you for inviting me to join this podcast with you. So in terms of my background, I guess, as you described, I'm an anesthesiologist by training. I have a PhD in neuroscience, and this ties in a little bit with some of the work we've done in lab animals, which also overlaps with my anesthesia training. I've worked in a few different places. So I trained in the UK originally. That's where I went to vet school. And then after that, I moved around a little bit to work in practice in small animal clinics, doing an internship, residency, and so on and so forth. But most of my academic careers has been in Canada now.
Thank you again for being here, Daniel. Now, you recently published a paper in JLAS titled Use of Loss of Writing Reflex to Assess Susceptibility to Carbon Dioxide Gas in 3 mouse strains. Can you tell us more about that?
Sure. Well, and I should start off, before I forget, I'm going to thank the students and trainees that worked on this project, because they deserve an enormous amount of credit for the time and hours they put in. So we had Brittany Monroe, Dexter Mernick, and Julia G, and they all played fairly critical roles or central roles in this. How did we get into this? I think, like much of my career, I've just kind of stumbled along and ended up doing this kind of work by chance as much as anything else. There wasn't any master plan in the background. Many years ago, we did quite a small study looking at carbon dioxide mixed with oxygen and pentobarb, just to look at how quickly each of those methods resulted in cardiac arrest and death. And we found some somewhat surprising results. And based on that, that's kind of expanded into looking at some of those areas in a bit more detail. And most recently, this carbon dioxide work. Why carbon dioxide in particular? It's still, I think, a fairly controversial euthanasia method. There are people who feel very strongly both for and against it, I think. I come at it, or at least I try and come at it fairly independently, because I'm not really from the lab animal world, and I'm an anesthesiologist by training. I don't have hugely strong feelings in one direction or another. I'm looking at it more from a scientific perspective in terms of this, this is quite interesting, and trying to understand better how it works and why it works, and can we do things to improve it, or are there things that are problematic with it? So one of the big controversies that's kind of plagued carbon dioxide for many years is, does it cause pain? And if it does cause pain, does that pain occur at a concentration where animals are more or less likely to be awake or aware or conscious of it? And that's for us, we felt that was one of the kind of big unanswered questions that might help us to make further progress with carbon dioxide.
Great. Thanks so much for kind of expanding on your background and giving us more of an approach to the study. And we also appreciate you recognizing your team, so thank you. So I think you may have answered some of this question, but it does appear over the past 10 years or so, there's been some great impactful scientific literature around CO2 and euthanasia, specifically in rodents. And I just wondered if you could maybe go a little further into how your study was somewhat designed differently than some of the others.
Sure. Much of the early work that really kind of caused people to pause and think about whether carbon dioxide use is acceptable or humane, much of that came from early work, also done in Canada, but in further west from me by Dan Weary at UBC, where he showed quite clearly that carbon dioxide is aversive to rodents. and that aversion occurs at fairly low levels or low concentrations of carbon dioxide. And then many others have built on that work and added to that work in the US and internationally, looking at different concentrations of carbon dioxide and what the response is in animals in terms of changes in their behavior. What we tried to do or tried to focus on was we tried to find outcomes we could identify and measure as at least semi-objectively. I think that's one of the things that's been very difficult in the past, and it makes it difficult to compare between studies, is lots of people have used lots of different ways to tell if an animal is conscious versus unconscious. And each of those methods has its pros and cons, and I'm certainly not claiming that our method is the best or the simplest to do. It's just one of probably one of the more common and more widely accepted methods that currently exists. So what we did, and we kind of went back to first principles, looking at the AVMA euthanasia guidelines and also looking at the human literature. We felt that using loss of righting reflex was probably one of the better options to pick from and to focus on in terms of identifying when animals may be unconscious. And the reason for that is that loss of righting reflex has really been the only outcome, as far as we're aware, that's been closely tied or very strongly correlated to what's measured in people. So in people, if you want to know if someone is conscious or unconscious, the standard method is to issue a verbal command. So very often you'll say someone's name and see if they're able to respond to that. And do they respond in the way that you'd expect them to? And the concentration of anesthetics that people are able or unable to respond to that verbal command is very closely correlated to loss of righting reflex in rats and mice. And so that's why we ended up kind of focusing on loss of righting reflex as our main outcome versus some of the others that have been used in the past.
Oh, great. Thank you. That really helps our listeners and our readers of our journal understand the loss of conscious, LOC, in your paper versus loss of righting reflex, LORR. So thanks for explaining that. So like me, I'm sure most of our listeners would want to hear more about your testing apparatus, and I say that emphatically. Could you please share your thoughts on the device design, especially how you incorporated the rotational velocity and CO2 flow rate variables?
Well, we were very lucky to work with an engineering student from the University of Guelph, Julia. And working with engineers is great because you kind of give them a problem that you're scratching your head about, and they're often very good at coming up with a solution, or at least a few different options to explore. And that's exactly what Julia did for us, or did with us. She came up with a design for a cylinder, and based on work I'd done in the past with testing righting reflex, we wanted to see, is there a way that we can assess the righting reflex without too much contact with the animal? Because we were worried, rightly or wrongly, that as soon as you interact with the animal, such as picking them up or moving them around, might that change the animal's response? So we tried to design a way that there was no contact with the animal by a person or by a gloved hand to test that righting reflex. And just to very briefly cover what the righting reflex is, or to remind people, we're putting an animal on its back, and we're waiting to see if the animal is able to correct its position or right itself. So that's what the righting reflex is. So when that's lost, that means the animal is on its back and it stays on its back. So in designing the cylinder or the container, we had a kind of clear perspex cylinder, which is just a piece of tubing that we bought from a hardware store. And then the end pieces or end caps were designed using computer-aided design software. Then those were then 3D printed, and we went through a fairly extensive phase of testing where we used different materials, tried different sizes, played around a little bit, and of course we had to work out, well, what's the right size of tube for a rat versus a mouse. So we had our little stuffed toy rats and stuffed toy mice that we used to test out the size of the chamber. And then we wanted to make sure that the motor that we were using to drive or rotate the cylinder could do that, consistently with different weights and different sizes of animals. So again, we tested our cylinder and tested a bunch of motors with different objects like tins of beans and that kind of thing. And I think we burnt out at least 1 or 2 motors in the process as we worked out what was the kind of best setup for us. So it's the testing process itself took a lot longer than the actual experiment because it took a while to kind of get things to a level that we were happy with.
Thank you for that. I loved hearing sort of some of the anecdotal behind the scenes, and I'm sure our listeners will as well. Following up on that, could you describe the 1 paw versus the 4 paw assessments for the loss of writing reflex? Our listeners are probably interested in hearing how you created and then also determined what those metrics would be.
Yeah, that was one of the hardest things that we did, and it was also one of the things that we found hardest to explain. It's one of these things that when you do it, it seems pretty straightforward and pretty obvious, and then when you're trying to write it down on paper without a video in front of you, it's hard. And we went back and forth on this for quite a long time. And in a second paper that we have coming out hopefully fairly soon, we added a figure in that paper to help explain it as clearly as possible. So one of the things we realized very early on is that even though it sounds very simple to say we measured the loss of writing reflex, there's no standard way to do this. For example, one group of researchers might say, well, the animal has to stay on its back for 30 seconds before we consider that they're unable to right themselves. And someone else might say, well, 5 seconds is enough, or 10 seconds is enough. Or so another group might feel, well, if they move one leg and they can touch the floor or touch the wall, that means that they've righted themselves. And someone else might feel, well, nothing can move at all. So even though we call it loss of writing reflex, the number of things that can vary within that identification or within that definition is pretty endless. So we came up with what we thought was reasonable for us. And again, this is not to claim that it's the only way to do it or even the best way to do it. But we did try and describe it in detail so that if anyone ever comes along to check our work or replicate it, they've got a good chance or reasonable chance of doing something that as close as possible to what we did. And in recognition of that variability in how people identify the loss of writing reflex, we came up with this idea of 1 paw versus 4 paws. And it was just a way to recognize that even within loss of writing reflex, we can be very cautious or conservative with our definition, or we can be quite liberal with our definition. So to think of it as simply as possible, with the 1 paw definition we used, the writing reflex is lost if no paws touch the container or cylinder walls at all. So the animal is completely on its back, all 4 limbs are in the air, nothing touches anything. None of the limbs touch the cylinder wall. If a single paw touched the cylinder wall or the container wall, we considered that the animal was moving towards righting itself. So we had the return or the presence of the writing reflex. And that's an extremely conservative definition. We're basically saying any kind of movement to touch a wall, there's a possibility this animal is conscious or aware of what's going on. And then the more liberal definition we took, which was the 4 paw definition, the writing reflex in that case was lost if up to 3 paws touched the container. So you could have anywhere up to 3 legs touching the container wall or the cylinder wall, and we still consider the animal unconscious. So they were only considered aware or conscious if all 4 of their paws were touching the container. So basically they're upright again. So we use those 2 variations in definition just to highlight that there's variability in how we define loss of writing reflex. And also when you're talking about something like euthanasia, you want to have as much confidence as possible that animals are unaware or unconscious when these things are being done. So we wanted to be quite cautious with our different approaches.
Great. Thank you again for describing that in such detail. I think our listeners are really going to want to know more about that variability and your team's approach to trying to kind of put some metrics around that. So moving more into kind of the methods of your study, you utilize 3 strains of mice
that we commonly use in research. And I wondered if you could kind of share your thoughts on why you picked these strains and how maybe other strains' results may impact.
Yes, I think exactly as you said, we picked these strains because they're commonly used. Ultimately, we felt, well, we have to pick something, and we have to start somewhere. Where do we possibly start? And the list of rat and mice strains it just goes on and on and on. So we thought, well, it makes sense to start with something that's common. Because those are the animals that most people will encounter in their work, and that will make the results that we find more relevant to most animals, hopefully. So we picked the C57 Black 6 as being the most common, or one of the most common inbred strains. CD1 is one of the most common outbred strains, and those are the two we kind of settled on initially. And then from asking around and speaking to colleagues in the lab animal world and pain research, we happened across the 129 P3J strain. And that one was interesting because it's a commonly used strain for creating transgenic lines, which I think is helpful in its own right. In addition to that, it's been found that it's a strain that has behaves slightly differently when it's being tested for during nociceptive testing. So it's a little bit more resistant to nociception through thermal or chemical means, but it's a little bit more sensitive to mechanical nociceptive testing. So we thought this third strain touched upon two interesting things. One is that it was common like the other two strains, but secondly, perhaps it might behave a little bit differently. So we thought this might be our kind of contrast strain, perhaps, to give us something a bit different from the C57s and the CD1s.
Oh, great. Thank you so much for that description. So as we move more into the results section of your manuscript, could you briefly discuss the need to expand your sample size in response to your initial data review?
Sure. When we perform a sample size, as I'm sure many people are aware, your sample size is your kind of best estimation of how many animals you might need on the assumptions that you're making behind your study. And because it's an estimate and because you have underlying assumptions, things might change. Your assumptions could be wrong, for example. So typically when we estimate a sample size, we're estimating it based on a few different things. One is our what we would consider statistically significant, or our alpha level, and that's usually fairly standardly set at p-value of less than 0.05. The second is how much power you want in your study. So how strong, as it were, do you want your study to be to find smaller differences between groups? And power is set at different levels, but what most papers tend to use is around 80% power. The two last things are the two things we can tweak a little bit, I guess. One is to decide how big a difference we want to spot. So we wanted to identify a difference of 2% between strains, for example. And that number of 2%, that's just based on what we think is reasonable. We could have decided that we wanted to identify a bigger difference of, say, 5% or a smaller difference of 0.5%. So it's a bit of a sliding scale. We picked 2% because we just felt that if the difference is smaller than that, so let's say C57s lost their writing reflex at 30% CO2 and the CD1s lost their writing reflex at 30.5% CO2, that small difference wouldn't really be that important or interesting or meaningful. Whereas we thought a difference of 2% or more might change how you approach one strain compared to another strain. So that's how we ended up with this 2% value. But we could have easily ended up with a value of, say, 3% or 4% or something else. And there's a bit of pragmatism to that as well. If you're trying to spot a very small difference, like let's say we wanted to spot a difference of 0.25% between strains, in general, you need a very large number of animals to spot very small differences. So at some point, other considerations like cost and time and resources come into play as well. So 2% was a good balance for us. And then the final thing that we have to consider when we're estimating our sample size is how variable do we think our data are going to be? And that's the part that sometimes is problematic, because if you're doing something that's not been done before or not been done much before, you might not know how variable your data are going to be. And the more variable your data are, the more animals you need to identify a difference. So we took our best guess based on existing literature as to how much variability we'd see in the loss of writing reflex, and we weren't quite right with our estimate. So we thought our data would be a little bit tighter or less variable, and what we found, especially in the C57 group, their results were more varied than what we predicted. And because of that increased variability, we then needed more animals to continue with our aim of identifying a 2% difference. So it's really because of the C57 data that we went from a lower sample size to a slightly higher sample size, from 28 to around 32 animals. And it was a bit weird, because when we completed the study and looked at all our results in the analysis, the variability was actually highest in the C57s compared to the other groups. Why that is, I don't know. We don't have an answer for that, but they certainly seem to behave a little bit differently compared to the other strains.
Great. Thank you again for that really detailed response. So as we jump into results and carrying on this question, you talked about the CO2 dose response curves for 3 mouse strains in your paper, and I'm wondering if you could please describe for our listeners what the EC50, the EC95 means, and how that correlated to sex and or strain differences.
Mm-hmm. So when you have what's called or thought of as a binary outcome, so a person or an animal can just exist in 2 states, for example, awake or asleep. So you're either awake or you're asleep, and there's not really anything in between, or not much in between. You can analyze your data to create a curve to work out the probability of a group of animals either being awake or asleep. And there's different ways to do it, but the way we did it was a type of regression analysis called probit analysis, and that allowed us to take all of the data points that we collected from each individual animal and plot them with a curve joining them up. And that gave us this curve that then allowed us to identify the EC95 and the EC50. So the EC50 divides the population in half by saying this is the concentration of carbon dioxide at which around 50% of animals will be awake or asleep. And the EC95 is the concentration of carbon dioxide at which 95% of animals would be asleep. And in our study, we presented both the values for the EC50 and the EC95, but what we really focused on was the EC95, because we felt it was more important to know what carbon dioxide concentration would result in most or almost all animals being asleep, so 95% of the population, because you want to have a carbon dioxide concentration that you have confidence or comfort in that is going to affect the majority of animals in the same way. So we had more confidence using the EC95 compared to if we'd made all of our discussion or drew all of our conclusions based on the EC50, where an animal would be either 50% in one group or 50% in the other group of being awake or asleep.
Great. Could you provide a high-level overview of your results? And we always want to know, did any of these results surprise your team?
Sure. So looking at it kind of a big picture level, probably the single most important thing is to think, was there a big strain difference? Because that's the thing that you worry about, is if there's a big difference between individual strains of mice in this case, that means that potentially some animals respond to carbon dioxide very differently compared to other animals. So that's probably the biggest thing. So focusing on the EC95 again, because that's what's appropriate for most of the population. The EC95 values between the different strains varied from around 20% up to around 31%. So that means there was a 10% difference in sensitivity to carbon dioxide between strains. So the most sensitive strain was the were the 129P3J animals, and the C57 black 6s were the least sensitive. So what that means is that the C57 black 6s required a higher concentration of CO2 to lose consciousness, whereas the 129P3Js would lose consciousness at a much lower concentration of CO2, so around a 10% difference. Why does that 10% matter? Because, and this is kind of the really big picture looking at our work, I guess, is does that 10% get us into a carbon dioxide concentration where animals might be experiencing pain before they become unconscious? And that's the part that it's hard. We don't have a clear answer to that now because we don't know what concentration animals feel pain at. But it certainly moves us a step closer to thinking maybe there are strain differences that could be important when we start to move on to the next step of animals potentially experiencing pain before they become unconscious.
Wonderful. Do you ever expect in our industry that there would be a different way to euthanize different strains and or sexes of rodents or mice even with CO2?
That's a very difficult question to answer, because in lab animal work, you're often dealing with groups of animals and potentially quite large numbers of animals in a given day or a part of a day. So whatever method is used, practicalities is such an important consideration. So it's a very different world from the world that I trained in, which is very much more clinical, where you're talking about client-owned or pet-owned animals, where you're working on one animal at a time for the most part. So you can really tailor things for the individual. Whereas in lab animal work, you're looking at it almost as a group or population of animals. So tailoring it down to strain differences or sex differences, I think it comes down to that balance between welfare considerations, practical considerations, and other resources such as finances, and also the strain or toll it takes on people doing this work as well. And it's kind of putting all of those things into the mix and coming up with what's the most acceptable balance of those different criteria. In terms of sex differences, certainly from what we found, it was interesting because we didn't set out to identify sex differences, so our study wasn't designed primarily to do that. So where differences may exist, based on what we saw, any differences that exist between male and female mice for these three strains were very small. The differences we found, it seemed that the females were consistently had higher values for their EC95s and EC50s, so their curves were shifted a little bit to the right. So there was a difference between the males and the females, but it wasn't a statistically significant difference. So it was something that we noticed that was interesting, but the difference was pretty small, less than 1% carbon dioxide concentration in most cases. So not something that we would particularly focus on or pay much attention on. In terms of the strain differences, and this is the part that's probably gives us more pause for thought, is if we have a 10% difference between the three strains, or the most and least sensitive of the three strains that we studied, are there other strains out there where there could be an even bigger difference in sensitivity? And that comes back to what I mentioned before. Are there some strains where carbon dioxide might be perceived or experienced as painful at a fairly low concentration long before they become unconscious? And that's the part that's still fairly unknown.
Oh, great. We really appreciate hearing a veterinary anesthesiologist's approach to this. And so thank you so much for explaining all of that. Okay, so last question. We ask this of everyone. Are you planning any follow-up studies in this area? I'm sure our listeners would want to know if your team has any plans to create similar studies for, say, rats and or other genetically modified mouse strains.
So we've, because of all the time and effort that went into designing the apparatus and testing it and destroying various things in that testing, it was kind of the natural step for us to go on and do rats as well. So we've completed our rat study, and that should hopefully come out fairly soon in AALAS. And the results from that are hopefully people will find interesting as well. And then the second thing we did, which I kind of touched upon right at the beginning, we found it quite disheartening, I suppose, looking at all the different ways to identify loss of writing reflex. So we thought, well, let's have a look at the literature and see how many different ways there are. And it pretty much was endless, which is a little bit depressing because it makes it very, very difficult to compare between different studies. Because if you make, if one study uses a 1-paw technique, someone else does a 4-paw technique, another group might use 30 seconds on their backs versus 15 seconds on their backs. It makes it very difficult to compare results and draw conclusions from those different studies. So we've also done some work just trying to describe how many different ways there are to measure loss of writing reflex and what that means in terms of doing this kind of work and how much we're able to repeat or replicate work, which I think is an important thing to consider when you're doing research, and it's a big problem in biomedical research where a lot of work is difficult, if not impossible, to replicate because people tend to tweak their methods so much.
Wonderful. Well, Daniel, we greatly appreciate you taking the time to chat with us today. I know our audience learned a lot. I know I did too. Now, for everyone else listening, we invite you to subscribe and leave us your comments and questions in the section below. Additionally, we invite you to consider submitting your current and future research to the AALAS scientific journals, JLAS or CompMed. You can also follow us on Facebook and Instagram or email us at info@aalas.org. We want your feedback. We can't wait to hear what you think about this episode. Finally, thank you for listening to the Last Word in AALAS podcast. Please be on the lookout for information on future podcast episodes dropping each month. Thank you.